Hi, welcome to Algebra 2 Common Core. Today we're going to be working on exponential function graphing. So if you don't have your graphing calculator with you, please pause the video and go get your calculator so that you can follow along on your calculator as well. Looking at the box on the top of your notes, you'll notice that we are going to look at basic exponential functions today. So basic exponential functions are functions that have the form of y equals b to the x. B is going to stand for the base of the exponential function. You'll notice the requirements on b. B has to be a positive number, and b cannot equal the number 1. So some examples of basic exponential functions would be the following. Y equals 4 to the x. Or we could have something like y equals 1/2 to the x. We can have any fraction as a base, so we could have something like y is equal to 3/5 to the x power. Or y equals 10 to the x power. All of these follow the form y equals b to the x, and it's really important that you can identify what an exponential function looks like. So you'll notice that the base is a number and the variable is in the exponent. So looking at our first example, we're going to sketch the graph of the function y equals 2 to the x. So let's start by making a table of values. We're given x's starting at -3. So remember that that just means 2 raised to the -3 power. Well, a negative exponent means take the reciprocal of the base, so that's the same as 1 over 2 cubed, which of course we know is 1/8. 2 to the -2 power is going to be 1 over 2 squared, or 1/4. 2 to the -1 power is going to be 1 over 2 to the first, or 1/2. 2 to the 0 power, remember that anything raised to the 0 power is equal to 1. And 2 to the first power is equal to 2. 2 to the second power is 4. Now we could keep going along in this manner, but we have enough points to graph. Taking a look at my table, I hope that you can recognize the pattern that we have for our y's. If I take any y value, to get the next y value, all I have to do is multiply by 2. So any y value gets doubled to get the next y value. And this pattern follows because I've got a base of 2 this time. Now go ahead and plot these points on the grid that you've been given. So -3 would be really close to the x-axis because its value is 1/8. -2, 1/4. -1, 1/2. 0, 1, so I can see that that's going to be my point that is the y-intercept, so I'm going to mark that on my table. That's the point where I'm crossing the y-axis. At 1, my answer is 2. At 2, the answer is 4. I might add one more in there because at 3, 2 to the third power is equal to 8. And I think we can fit this on our graph as well. So connecting these points, you'll notice that this graph comes really close to the x-axis, but it doesn't cross the x-axis. I made mine a little curvy there, but it should flow right along and be an increasing function. I'm even going to write that down. This is an increasing function, because I see that as the x's get bigger, the y gets bigger and bigger. I can also see that the graph of it goes uphill. So let's look at our domain. Since the domain is the list of all x values that are possible. I can put any number in for the exponent x. So that tells me that the domain is going to be all real numbers. As an interval, we could write that as negative infinity to positive infinity. My range, however, if you look at the table of values or you look at the graph, you should recognize that there's no negative answers. The other thing we should note is that we never get 0 as an answer. So therefore the range begins at 0, not including 0, so that's why I'm using a curved parentheses at 0, and goes up to positive infinity. We could also write this in set builder notation as y such that y is greater than 0. Because my graph comes really close to the x-axis, but it doesn't ever touch it, I'm going to call the x-axis an asymptote for this graph. Make sure you spell that correctly. An asymptote is a line on a graph that the graph comes very close to, but it doesn't ever touch. Now I'd like you to pause the video and also enter this function into your graphing calculator. You can use a Zoom 6 window on your calculator and see that the graph on the calculator should match what we have on our graph in your notes. Let's go ahead and look at the next exercise. We want to fill out the table and sketch the graph for the function y equals 1/2 to the x power. So let's carefully evaluate these values with an input of -3. I want to say 1/2 to the -3rd power. So a negative exponent just means that I'm going to take the reciprocal. So that means the same as 2 to the 3rd power, which of course is 8. Let's do a -2 exponent. So 1/2 to the -2 is going to mean the same as 2 to the 2nd power, which is 4. 1/2 to the -1 power means 2 to the 1st power, which is 2. 1/2 to the 0 power is equal to 1. 1/2 to the 1st is equal to 1/2. And 1/2 to the 2nd is equal to 1/4. So we see similar numbers, but you should notice a different pattern for these. So at -3, my answer is +8. So let's plot that point. At -2, I've got 4. At -1, we have an answer of 2. At 0, the answer is 1. At 1, we have 1/2. And at 2, we have 1/4. So connect those points. And again, you should see that this graph also approaches the x-axis but doesn't cross it. Our domain is still going to be all real numbers, so I'm going to write that in interval notation as -infinity to infinity. The range still stays the same, everything above the number 0 but not including 0. This one also has an asymptote. The asymptote is also the x-axis because the graph is coming very close to the x-axis but not crossing it. You should also notice on your graph that actually the y-intercept, while I didn't graph it very well, the y-intercept is the same point that it was on the last graph, 0, 1. We can call this graph a decreasing function. If we look at the graph, we see that it goes downhill instead of uphill. It's going to be important for us to be able to recognize which ones are going to be decreasing functions and which exponentials are going to be increasing functions. For exercise number 3, we're going to have a little bit more complicated function. Now I've got y equals 7 times 3 to the x power. Now when I look at that function, the exponential portion is similar to what we had before, a base raised to a variable exponent. But you'll notice that this time I've got a coefficient. The 7 is being multiplied by 3 to the x. Now we would never, in a case like this, multiply the 7 times the 3 before raising it to the x power. We of course have to follow the order of operations and do the exponent before we do the multiply. So don't be tempted to multiply the 7 times the 3. Let's make a table of values for this one as well. So I'm going to use similar values for my input. Let's start with -2, -1, 0, 1, and 2. So this is going to be 7 times 3 to the -2. So that's 7 times 1/9, or 7/9. For -1, we want to say 7 times 3 to the -1, so that'll be 7/3. 7 times 3 to the 0, well 3 to the 0 is just 1, so 7 times 1 gives us 7. 7 times 3 to the first, do the 3 to the first first, so 7 times 3, 21. And 7 times 3 to the second would be 7 times 9, which is 63. Now it says make sure that we are determining the y-intercept algebraically. So that's just saying whenever we want a y-intercept, we're going to substitute x equals 0. So we just did that mentally. Let's show our work for that. So y is equal to 7 times 3 to the 0 power. But 3 to the 0 is 1, so 7 times 1 is 7. Now on my graph, I want to take note of the values in my table of values, and I notice that I'm starting with much smaller values of the output and going to much larger values. So that tells me that this one is also going to be an increasing function, and that's exactly what question B is asking us. It is an increasing function, and in a minute we'll come back and look at why it's an increasing function. So let's label some points on our graph. On my y-axis, I think I'm going to count by tens and just mark a few of them. On the x-axis, it's fine to go by ones. So take a minute to plot these points and come back and check with my graph. Also enter it into your graphing calculator. In the graphing calculator, you're going to have to adjust your windows so that you can see values as big as 21 and 63. So of course that means that you're going to change the y max to a larger number to accommodate those bigger outputs. So stop the video for a minute and come back and check your answer when you're done. Compare your graph with mine. And make sure that you've also labeled the y-intercept. So the y-intercept should be 0, 7. Also take a look at your graphing calculator and hopefully you'll see the same graph there. For our last function, we're going to graph the function y equals 1/3 to the x power plus 4. Now let's look at question A. How does this function's graph compare to that of y equals 1/3 to the x? Let's think about what adding 4 does to the function's graph. Remember that we're really adding 4 to the output of the original function, so adding 4 should mean that my y values are 4 higher. So that means that we are going to shift this graph up 4 units. So I'm going to make a table of values that also includes y equals 1/3 to the x, and then see the change in the output when I add 1/4 on. So there's my x column. My first column is going to be 1/3 to the x, and my next column is going to be 1/3 to the x plus 4. So let's take values from -2, -1, 0, 1, and 2. At -2, 1/3 to the -2 power, the negative exponent tells me take the reciprocal. So that's the same as 3 to the second power, which is 9. 1/3 to the -1 will be 3. 1/3 to the 0 is 1. Hopefully you're noticing the pattern here is multiply by 1/3 or divide by 3. When my exponent is 1, I've got an answer of 1/3. And when my exponent is 2, my answer is 1/9. Now for the last column, all we're going to do is add 4 to each of those outputs. So 9 plus 4 is giving me an output of 13. 3 plus 4, output of 7. 1 plus 4, that'll be 5. 4 and 1/3, 4 and 1/9. So graphing, I'm again going to shift my graph up 4 units. So the highest value on my y-axis is 13. I think I can probably count by ones for that one. So at -2, I need 13. -1 is 7. At 0, my y-intercept is 5. At 1, I should have a little bit above 4, 4 1/3. And at 2, I'm barely above the number 4. So this graph looks something like this. Now you'll notice that this time the graph is coming closer and closer to the answer of 4. So I'm actually going to draw in a dotted line here along 4 because my horizontal asymptote, my asymptote that happens to be a horizontal line, is y equals 4. So this one comes closer and closer to an answer of y equals 4, but it doesn't ever achieve that answer. Label your y-intercept. So that point is 0, 5. Now let's take a minute to summarize what we have found from our graphing. When we have a graph that is showing growth, by growth we mean that it is an increasing function. If you take a look at the examples that were increasing functions, I hope that you recognize that that always occurred when the base number was bigger than 1. So every time I have a base, the number that's being raised to the power, and it's bigger than 1, my graph should increase. So it should be an uphill graph. The opposite of an increasing function, or in terms of exponential functions, the opposite of a growth graph, is called a decay graph. Some of you may have heard of these in chemistry, for example, with half-life problems. Decay is going to be a decreasing function. And it's a little harder to recognize how we get a decreasing function with exponentials. But if you look carefully, you'll notice that the base values were always fractions whose value was less than 1. But because we've got an exponential function, we also have to make sure that the base is bigger than 0. So this just tells us that we're going to have a decreasing function, or we will have exponential decay, anytime the base is a fraction whose value is between 0 and 1. Now, of course, I could also write it as a decimal with a value between 0 and 1. So, for example, if I had y equals 0.75 raised to the x power, this would also be a decreasing function showing us exponential decay. Let's just take a minute to compare exponential growth and decay functions. So in your notes, let's put a couple more examples. If I have, for example, y is equal to 6 to the x power. Because the base is 6, and that's a number bigger than 1, I know that this would be exponential growth. If I have the function y equals 5/2 to the x power, while that's a fraction, its value for the base is bigger than 1, so since the b is bigger than 1, this function would also represent exponential growth. If I have something like y is equal to 0.9 to the x power, this time the base is less than 1. Notice that it's between 0 and 1. So that would be an example of exponential decay. One more, let's take a look at y equals 2 to the negative x. Well, I can't decide whether I have exponential growth or decay unless my exponent is just the variable x. So I'm going to rewrite this as 1 over 2 to the x power. And now, since my base is a number that's less than 1, this represents exponential decay. In class, we're going to do some more practicing with exponential growth and decay functions. So practice with your calculator. Make sure that you can see these graphs on your calculator. And we'll see you tomorrow.